In this video, we'll be going over work, power, and energy for the topic 1 of impulse and momentum for AP Physics 1. So let's start off with what is momentum. Momentum is inertia in motion, and it can be represented with the equation of the vector of P is equal to mass times the vector of V. So this is a vector, momentum is a vector quantity, and it has the direction of velocity because that is the only vector that it's being multiplied by. And its units are measured in kilograms dot meters per second. And a critical concept that you have to know about of momentum is that large mass or a large velocity will result in a large momentum because they're both being multiplied by each other. So they're directly mass and momentum and mass are directly related, and also momentum and velocity. And also you need to know that objects at rest have zero momentum because there is nothing in motion and the object is just staying still. Next, let's talk about what is impulse. So impulse is the change in momentum. And you can think of impulse with this example. Let's think of a force time graph, and let's inspect the area under its curve. So let's say this is the graph, right? And we have something that looks like this. So this, we can divide this triangle, this composite shape into 3 shapes, and then we find the area of each individual shape in order to calculate the impulse. And something that you need to know is that impulse is the area under the force time graph. So essentially, let's calculate this. So this is going to be, say this is 1, 2, this is supposed to be T, 3, 4, 5, 6. Now, we know that the area of a triangle is going to be 1/2 base times height. And we know that the area of a rectangle is going to be equal to length times width. So we can just calculate the area of 1. So that's going to be a triangle. So that's 1/2 times 2 seconds. Time is measured in seconds, and force is going to be measured in newtons. And so that's going to be 1/2 times the base, which is 2 seconds, times 5 times, okay, forgot to label this. So this is going to be, let's make this 5. Let's actually make, yeah, that's going to be 2. So, okay, so 1/2 times 5 newtons is going to, and the area is going to be just 5 newtons per times seconds. And the area of 2 is going to be 5 newtons times the width. So that's going to be 2 seconds. So that's going to be 10 newtons times seconds. And then area 3 is going to be the same as the first. So that's this. That's going to be 5 newtons times seconds. And now the total impulse can be calculated like this. So just 5 newtons times seconds plus 20 newtons times seconds plus 10 newtons times seconds. So in total, we have the total area under the curve is just 35 newtons times seconds. And this is also equal to 35 joules. So now let's talk more about what impulse really is. So impulse can be represented with the formula, the vector of J is in units J, and is delta P. So that's change in impulse. Or it can also be represented as J is equal to the vector of F times delta T. And it's measured in the units of newtons times seconds, which is also equal to kilograms times meters over seconds. So now let's highlight this and let's talk about what the impulse momentum theorem is. So what the impulse momentum theorem is a statement that the vector of F times delta t is equal to delta p. And expanded, this is just vector of F times delta t is equal to m times the vector v the final velocity times mass times initial velocity. So what this means is that a large force times short time is the same thing as a small force times a long time. So these will have the same impulse. And now we can talk about the force-time relationship. So what you need to know is that force and time are inversely related. So what that means is that, let's say you increase collision time, then this will decrease force. And let's say that you decrease collision time. Well, this will increase force. So this explains, in real life, you can think of the examples of airbags, helmets, and also crumple zones. So let's expand on what like an airbag analogy really means. So think of like the deflation of the airbag takes time, and this reduces the force. So like more time, less impact is basically what you can think of like happens in real life. So the deflation equals time. So then the force decreases. So that's essentially a concept that you really need to know. Let's talk about impulse in collisions. Okay, so what you need to know is that during collisions, forces are equal and opposite according to Newton's second law. And the time of contact is the same. Because think about it, they touch each other at the same time, because otherwise they wouldn't collide, because they have to be touching each other at the same time. So that means that therefore, this symbol means therefore, impulses are equal and opposite, because you can think of like this occurring at one instance, like this action occurs at one instance. So delta impulse P1, we represent that as P1 subscript, is equal to the equal and opposite delta P2. So now let's talk about the law of conservation momentum. So what this means is that in the absence of external forces, total momentum is conserved. So what this means is that symbolically we can write delta P vector before or initial is equal to, the summation. These are summation, not delta. P at final. So you also need to know what an external force is. So an external force includes gravity and also friction. And you need, and if if these are negligible, that means that momentum is conserved because there's no external forces acting on the system. So you can think of of before the collision, we can draw this out. So let's say you have two masses colliding with each other like this, and then the collision looks like this. And then after the collision, as you know, you slide them together, then they just they go in the opposite direction. Oops. V2, and this is this little thing is like, it means final. Okay. Like that. We can also like draw this out like this. So here's another diagram that you can think of. So think M1, M2, and then these two collide together like this, and P initial is equal to MI UI. This is the derivation of the law. PI is equal to M2U2. So then after the collision, then they will look like this. So you can essentially think of them like swapping. And represent this with V. V2, and then we can represent this entire thing with an equation like this. Now, yeah. So now let's talk about types. Okay, let's talk about types of collisions. It's kind of getting a little, okay. Types of collisions. So let's say we have stick, aka perfectly inelastic collisions. So what this means is that you have two objects before, and then after you have one object. So what this means is, as the name alludes, you have one object in the end because they stick together. So this can be symbolically represented as M1 V1 initial plus M2 V2 initial is equal to M1 plus M2 times VF. And something to note about this type of collision is that kinetic energy is not conserved. So drawing this out, what this essentially means is that since the objects stick together, they share the same velocity after the collision, is basically what this formula represents. So we can draw this out like this. Let's say, okay, we need two balls, M1, and this is going to be our M2. So before, what's our collision? So before, let's see, they're both like moving towards each other. So they both have their own respective velocities, and they're moving like that. And then afterwards, they will stick together like this. So they're stuck together, and now they're both moving with the leftover velocity essentially, and they're just one mass, and you combine them together because they're now just one object. And so here we have two objects that approach and collide. And then here we have that they stick and move together. So that is how you can see that they have a combined mass, and they also have a common final velocity, because as you can see that they're just one object now, so you consider it as one object. So now let's talk about, highlight this, and let's talk about the second important collision that you have to know. So we have the explosion collision, which is basically a backwards inelastic collision. And what this means is that before you have one object, and then after you have two objects. And something you know is that initial momentum is often 0. So symbolically, we can write 0 is equal to m1 times v1 plus m2 times v2. So to draw this out, we can imagine that, let's say you have this. Let's say you have like a bomb. And let's say that it's being lit like this. And that means before the explosion, your momentum is equal to 0. But then, let's say after, after the explosion, your momentum also is equal to 0 because it's all broken up. Say you have it's all scattered like this. And then all the pieces, they go into their respective directions. So it's all scattered. And here, let's also think of like a gun. Say you have like a little pistol right here, right? So this is before you fire, and the gun is just like this. But then after you fire, the gun is gonna launch backwards, and then the bullet is gonna launch forwards. So, okay, this is not one piece. Okay, so, and also, let's also think of like, a classic example is a cannon. So, say you have a cannon like this. And before the explosion, the ball is like in there. But then after the explosion, the ball like shoots out. And then it's like this. It's like a gust of wind. And let's see a homemade cannon, like a cannon like this. It's like constructed to deliver an impulse to a tennis ball and then accelerate it forward. So the cannon, it experiences an equal and opposite impulse, which accelerates the cannon backwards. So you can see that. So the momentum change of the tennis ball is equal and opposite to the momentum change of the cannon. So now we can create like a comparison chart, like between elastic and inelastic collisions. So what you need to know is that elastic, inelastic. Let's talk about the momentum and the kinetic energy. So let's talk about whether or not and perfectly inelastic. So in all of these, momentum is conserved. So okay, check is for conserved. And kinetic energy is also conserved in elastic, not conserved. And then minimum kinetic energy. So momentum is conserved in all collisions, and kinetic energy is only conserved in elastic collisions. So let's do some practice problems with this now. So let's say that you have a 40 kilogram hockey puck that experiences a constant force of 120 newtons for 0.015 seconds. And let's find out what impulse acts on the puck. And also let's find if the puck was initially at rest. Let's find its final speed. So we can use the formula J is equal to F times delta T, and then your impulse is going to be 120, which is the force, times the time, which was 0.015 seconds. So in joules, this is going to be 1.80 newtons times seconds. Now for this, for B, we can use the impulse momentum theorem, which again is that J is equal to delta P, and that's going to be equal to m times VF minus m times V initial. And also, since we know that V initial is equal to 0, we substitute that in. So we know that the impulse from earlier that we calculated, J is equal to 1.80 newtons times seconds, so we plug that into here. And we know that 0.40 is the mass, and we know that the velocity is what we're solving for. So dividing both sides by 0.40, VF is going to be equal to 4.5 meters times seconds. Now let's do another problem on perfectly inelastic collisions. So let's say that we have a 2.0 kilogram cart moving at 6.0 meters per second, and it collides with a 4.0 kilogram cart at rest, and they stick together. So find their final velocity. So in order to do this problem, we have to remember the relationship m1 times v1 initial times m2 v2 initial is equal to the sum of their masses times the final velocity. So think of this as object 1, object 2, and then object final. So now we just plug all of our variables in. So 2.0 is m1 times 6.0 velocity that it had, plus 4.0 times 0 is equal to 6.0 times VF. Simplifying this, we have 12 plus 0 is equal to 6 VF, and 12 is going to be and dividing both sides by 6, we have that VF is going to be equal to 2.0 meters per second. Now let's do a problem about explosion / recoil. So this is gonna be a backwards inelastic. Okay, so let's say that we have a 5.0 kilogram cannon ball and it fires a 0.050 kilogram cannonball horizontally at 200 meters per second. So find the recoil speed of the cannon. So this is a little tricky, but we just use, by recoil speed, they just mean the velocity. So don't get tripped up by that. So what we need to remember is that the initial momentum is equal to 0. So we can use the equation 0 as our momentum and then write m1 times v1 plus m2 plus v2. And we can also let the cannon recoil be negative because of Newton's second law. So we have 0 is equal to 0.050 as m1 times 200 velocity plus 5.0 for m2 times v. So that means that simplifying this, we get 0 is equal to 10 plus 5v, and then dividing both, isolating for 5v, we have 10. 5v is equal to 2.0 meters per second backward. Remember, it's backwards because it has to go in the opposite direction. And actually this is negative. So it's actually v is equal to negative 2.0. And then the direction is backwards. You have to specify that. And so we have 4. That's the interpretation of the negative sign. So let's do a question on collision and also impulse. So let's say we have a 60 kilogram skater moving at 8.0 meters per second, and it collides head on with a skater moving at negative 4.0 meters per second, and they stick together after their collision. So now let's find their final velocity, and then B, let's determine the impulse on the 60 kilogram skater. So in order to do this, we can start by using the relation that we used earlier. Let's just bring this down. I think we wrote it up here. Okay. Actually, let's just, So we have 60 kilograms for the mass times 8.0 for the velocity plus 40 times for the mass of the second object times negative 4.0 for the velocity, and that's going to be equal to 100 because we know that their total mass is 60 plus 40 is 100, and then times VF. So this simplifies to 480 minus 160, that's equal to 100 VF, and then VF is going to be, simplifying this is 320, what am I saying? Yeah, divided by 100 VF, and VF is going to be equal to 3.2 meters per second. So now for B, we can set impulse is equal to the relationship of m times VF minus VI. That was just this side right here. And plugging in our variables, we have 60 times 3.2 minus 8.0, which is the final and initial velocity of the 60 kilogram skater. That's going to be equal to 60 times negative 4.8. And then the impulse is going to be negative 288 newtons times second. And the negative sign means the impulse is opposite the original motion. And that's about it. Thanks for watching.